Hello everyone, welcome back to another video. We are now in 8.1, which is discussing the graphs of what they call quadratic functions. Quadratic functions just means that you start with x to the second power. So anytime you see the second power, that is what they call a quadratic function. The graph is this U shape over here, which is called a parabola. Now I want to discuss what they call the parent function first, before we start talking about example 1. The parent function, and for those of you guys asking what in the world the parent function is, it's the original function, okay? Well, what's the original function look like? Like we said, it's a parabola or a U-shape, but the name of it is a parabola that opens upwards. And it has a lot of points, but I put some main points over here that you might want to jot down somewhere. The first point being 0, 0, the origin. You have negative 1, 1. You have positive 1, 1. Then you have 2, 4, and also negative 2, 4, and then also positive 2, 4. So notice that these points are the same thing. They're just on opposite ends of the y-axis, right? And let's talk about some things that the parent function has. The parent function has what they call the vertex. The vertex is either one of two things. Either it's the lowest point on this parabola, this U shape, which is on the very bottom, which explains why it's 0, 0. It has what's called the axis of symmetry, which I mentioned to you guys before. Axis of symmetry is a line that cuts this thing into two equal halves. So this red dotted line that you guys see right here cuts this U shape into two equal halves. That is the line x equals 0. And the last two things for your parent function, also the most difficult things to understand, is domain and range. Domains represent your x's, range represents your y's. When they ask you guys for the domain and range of a graph, let's start with domain. When they ask you guys for the domain of a graph, since domain represents your x values, they're asking you how far to the left your graph goes and how far to the right it goes if it were to continue on and on forever. So domains are your x's. X's go left and right. So I'm checking out my graph to see how far it goes to the left and how far it goes to the right. Let's focus on the left side first. Notice that your graph goes up, but it also goes up and to the left, right? If that were to continue and it goes left on and on forever, it would hit the number negative infinity. Negative is on the left side. Infinity meaning it goes on and on forever. Now, if you look at the right side, yes, it goes up, but it's also going to the right. And if that continues on and on forever to the right, it would hit positive infinity. So your domain is negative to positive infinity. You can also say all real numbers or all reals, okay? Now let's talk about your range. Your range represents your y values. Your y's go up and down. So when I ask you for the range of a graph, I'm asking you how far up it goes and how far down it goes. Now if you take a look at your graph, see how these lines continue up and up forever? So they will go all the way up to positive infinity, because for your y values, if you go upwards, that's in the positive direction, right? So this goes up and up all the way to positive infinity. The question is, does it do the same thing going down? If you guys take a look at this graph, it actually curves. It stops at a point. The very lowest point on this graph is 0. So it starts at 0 and goes all the way up to positive infinity. Now, for those of you guys asking, how come 0 has this bracket and infinity sign has a parentheses instead? Bracket means it's part of your graph. It's a point on the graph. And if you guys notice, 0, 0 is a point on my graph. So any point that's part of your graph will always get a bracket. The infinity sign will always get a parentheses because it's not just one point, it's many, many points, okay? So that's it for your parent function. So now let's compare it to what they want to do in example 1, which is graphing ax squared, as in you will have a number in front of your x squared term. Here it's the number 0.5, here it's the number 2. It's our job to figure out what these two numbers do to the parent function, okay? And in order for us to determine that, I'm going to do what they call a t-chart. I'm going to plug in some x values in order to solve for y, and I'm going to plot those points to see how it's related to the parent function. Notice that this graph has negative x values. It also has positive x values, meaning you probably want to pick some of both. So let's just pick, let's pick negative 2, negative 1, my favorite point 0, and then 1, 2. We got some negatives, we got some positives, and we got the number 0. More than likely, I'll pick the same points for part B. So I'm going to plug this into this equation to figure out what my y is, and then I'm going to plot all of these points. All right, you guys ready? Here we go. Keep in mind f of x, I wrote over here, f of x is the same thing as y. So if you plug in negative 2, let's see, it'll say 0.5 negative 2 squared. If you plug in negative 1, it'll say 0.5 negative 1 squared. If you plug in 0, it'll say 0.5 0 squared. You plug in 1, it'll say 0.5 1 squared. And finally, you plug in 2, it'll say 0.5 2 squared. So all I did was replace these x's with negative 2 all the way to positive 2. Now let's solve these real quick so we can go ahead and graph this thing. Be very careful here. There's a common mistake where people love to multiply these numbers first and then raise it to the second power. Keep in mind PEMDAS, which we use for order of operations, it tells us before you multiply to deal with the exponent first. So I'm going to deal with this thing first before I multiply by 0.5. So you have negative 2 squared, which is 4. When you multiply 4 times 0.5, keep in mind 0.5 is a half, right? What is a half of 4? Well, a half of 4 is 2. So when you take positive 4 and multiply it by 0.5, the answer is 2, because 0.5 literally means half of that number. So half of 4, 2. Let's try that with the next one. You have negative 1 squared. Keep in mind we're doing the exponent first before we multiply. You have negative 1 squared, which is positive 1. Well, half of 1, isn't that a half or 0.5? I'd much rather use decimals when it comes to graphing instead of fractions. Then you have my favorite point, 0 squared 0. 0 times anything is still 0, hence why it's my favorite point, because you always get 0 back. And then you have 1 squared, which is 1. Again, a half of 1 is a half, which we'll say as 0.5. And then finally, you've got 2 squared, which is 4. A half of 4 is 2. Notice how you're getting the same numbers back, which makes sense because if you look at the parent function, the original graph, it's the same points on both ends. It's just one's the negative version, one's the positive version. All right, so here we go. We've got 1, 2, 3, 4, 5 points to graph. So let's graph this thing and see what it looks like. So let's plot some numbers on here first. All right, my first point is negative 2, comma, positive 2. So left 2 and up 2. Then you have negative 1 and 0.5. So negative 1 and up a half. Then you've got 0, 0, my favorite point. Then you've got 1 and 0.5. So right 1 and up a half. And then your last point, 2, comma, 2. So right 2 and up 2. Connect the dots. And you have your graph. Now, right now, if you were to compare them, you can kind of sort of tell that this one's slightly wider than your parent function, right? But let me go ahead and graph some of the parent function points into this one so you guys can compare the two. So your parent function had 0, 0, so they had that in common. It also had negative 1, 1 and positive 1, 1. And if I connect those dots, here is the parent function in green. And now you guys can clearly see that this graph, when your a value, a is the number from the x squared, when your a value is a half, that this graph becomes wider, doesn't it? So that's what they wanted you guys to discover. Now let's see what happens if your a value is the number 2 instead. So we're going to do the same thing. I'm going to pick the numbers negative 2 to positive 2 for my x values. I'm going to plug it in to see what we get for your y values and then graph those as well. All right, so here we go. Let's make some room for this thing. Okay, so here's my t-chart. I'm going to pick the same numbers, negative 2, negative 1, 0, 1, and 2 for this equation. All I'm going to do is replace this x with these 5 numbers. So here we go. So you got 2 times first number, negative 2 to the second. You've got 2 times negative 1 to the second. You've got 2 times 0 to the second, 2 times 1 to the second, and 2 times 2 to the second. So again, all I did was replace this x with negative 2 all the way to positive 2. Now let's solve these to see what your y value would be. Again, using PEMDAS for order of operations, deal with the exponent first before you decide to multiply. So you get negative 2 squared, which is 4. 4 times 2 is 8. You have negative 1 squared, which is positive 1. 1 times 2, 2. Then you've got 0 squared, which is 0. 0 times 2 is still 0. Again, my favorite point for that reason. You have 1 squared, which is 1. 1 times 2, 2. And here you have 2 squared, which is 4. 4 times 2, 8. So these are your 5 points we're going to graph. And then we'll compare it to the original, what they call the parent function, to see how that one is different. So here we go. So let's plot some numbers. You've got -1, -2, +1, +2. For your y's, this thing goes all the way up to 8. So 1, 2, 3, 4, 5, 6, 7, 8. So you've got -2, 8 all the way up there. Did I plot that one right? Okay, there's that point. You've got -1, 2. You have 0, 0. You have 1, 2. And then you also have 2, 8. Again, way up there. So connect the dots. And there is your parabola for that graph. Again, what I'm going to do is draw the points for the original parabola, the parent function, so you guys can compare and see what the difference is. So here, let's plot our points. So your parent function also has 0, 0. Let's see, that also had -1, 1. And it had +1, 1. And if you connect those dots, you'll see that instead of it getting wider like the first one did, this thing actually got more narrow, or you can say skinnier instead. So from this, we need to figure out like what's happening with our a value when it gets wider and when it gets skinnier. So based on what we've seen so far, you've got a value less than 1, you've got a value bigger than 1. So what happened when your a value was less than 1? It got wider, didn't it? And then what happened when your a value was bigger than 1? Well, look at your green graph. What happened? It got more narrow, or you can say skinnier. So when a is bigger than 1, it gets more narrow. Or you can use the word skinnier, whatever's easier for you guys to use. So from this example, we should have learned if your a value is less than 1, it gets wider. If your a value is bigger than 1, it gets more narrow, or again, you can say skinnier. We don't use the number 1 itself, because if you were to have 1, you would just get the original function. It would be the same. Because 1 times x squared is still x squared, so nothing would change. All right, that's all we have for this video, guys. In the next video, we'll discuss transformations of this graph, which means when to move this thing up, down, left, or right. All right, we'll see you guys in the next one.